Welcome all for this session where we are going to discuss the instrumentation of UV spectrophotometer. So far we have discussed in the previous sessions about the theoretical aspects of UV spectroscopy. This session will be covering the instrumentation aspect of UV spectroscopy. Coming to the instrumentation, there are three different types of UV instruments that are available. The first one is photometer, the second one is colorimeter, and the third one is spectrophotometer. All these three instruments, no matter, are being used in UV visible region, but the kind of wavelength selector and the kind of detectors what they employ in each are quite different. Coming to the photometer, this is an instrument that measures the ratio or some function of 2 of the radiant power of electromagnetic beams, and the filter is used as a wavelength selector here. This isolates a narrow wavelength region from the entire electromagnetic spectrum, and this photometer usually has photocell or the phototube as detector, and the wavelength region what it covers is both the UV as well as the visible region. And when compared to the colorimeter or when compared to the spectrophotometer, this photometer, the band pass or the wavelength region which it allows through is quite broader. Okay, it allows more than 20 nanometer, 20 to 30 nanometer wavelength region to pass through. So compared to the spectrophotometer, the photometer is not that efficient instrument. Coming to the next one, that is colorimeter. Colorimeter is almost the same as the photometer, but it works only in the visible region. And commercially available photometers are called as colorimeters. And just to have a visualization, this is the digital photometer which is available, and this is a digital colorimeter which we will be using in our day-to-day practicals. Coming to spectrophotometer, the spectrophotometer, they measure the ratio or a function of the 2 of the radiant power of 2 electromagnetic beams over a large wavelength region, whereas the photometers, they are not measuring over the large wavelength region, but here we have a very large wavelength region for measurement. And here the wavelength selectors that we use are monochromators, whereas in the previous they will be there were the filters which were used as the wavelength selectors. Here we use monochromators, either prisms or gratings, and they cover larger wavelength region, and they employ very sensitive detector like phototubes or photomultiplier tubes. And the photomultiplier tubes is a kind of detector which is the sensitive among the available detectors, and we use the most sensitive instrument or the sensitive detector in the spectrophotometer. And the spectrophotometer instrument is much reliable and accurate, precise compared to the previous two, that is photometer and colorimeter. Coming to the instrumentation or the components that we have in an UV spectrophotometer, we will be discussing UV spectrophotometer rather than photometer or colorimeter. The components what we find in UV spectrophotometers are the source of radiation, the monochromators or the wavelength selectors, the detectors, the recording systems, the sample cells, and we have something called as match cells in the sample cells. Coming to the radiation sources, we have altogether 5 different radiation sources. All of them produce the radiations falling in UV visible region, and there are some ideal requirements which we expect from any of these radiation sources. What are the ideal requirements? We will go through one by one. The first ideal requirement is they should be stable and should not fluctuate. It's a very basic requirement what any radiation source should have. It should be stable and should not fluctuate. I mean to say, the intensity and the wavelength what they are emitting or producing should be stable and should not fluctuate. It should emit the light of continuum spectrum of high and uniform intensity over the entire wavelength region in which it's used. Suppose if you are scanning from 200 to 300 nanometer, the source whatever you are using, they should constantly emit the wavelengths covering from 200 to 300 nanometer, and the source should be sufficient or the output should be of sufficient intensity, and it should produce a continuum spectrum rather than a line or a band spectrum. That is a very critical or crucial requirement any instrument should possess, or any radiation source should possess. And the next ideal requirement is it should provide an incident light of sufficient intensity for transmitted energy to be detected at the end of optical path. So what this means, the intensity of the incident light should be sufficient enough so that it can be seen, or it can be checked, or it can be detected after it is being transmitted through a sample cell. I mean to say, the intensity should be sufficient enough. It should not show any fatigue or on continuous use, or it should not show any intensity fluctuations, or it should not change the wavelength on a continuous usage. So these are the basic ideal requirements any radiation source should possess. And we have 5 radiation sources which we use in UV spectroscopy. The first is tungsten lamp, the second one is hydrogen discharge lamp, the third one is deuterium lamp, the fourth one is xenon discharge lamp, and the fifth and the last is the mercury arc lamp. We'll come through these radiation sources individually, one by one. Coming to the tungsten lamp, it is very much similar to that of electric bulb, what we use, the incandescent electric bulb at home. And this tungsten lamp produces radiation in the wavelength region of 320 to 2500 nanometer. And these lamps are usually very robust and stable and very easy to use. And they generate or produce a continuum source of light, which is very much ideal requirement which we expect out of any radiation source. And the tungsten filament is usually heated electrically to white heat. You can see this image where there is an evacuated glass tube inside which we have an inert gas, and there are 2 electrodes joined by an filament here made up of tungsten, and this tungsten filament is heated with a source of electric energy, and we heat it up till 3000 Kelvin or much beyond that. And what happens, once after we heat up till 3000 Kelvin, the radiation or the filament will start eliminating the light, and we use that light which is in this particular wavelength region. One of the disadvantages of this light source is the major portion of radiation what it produces, it falls in the near IR region. I mean to say, it falls out of the UV visible region and it overlaps on the near IR region. That is, after 800 nanometer, if you keep on going, then it is the near IR region of the electromagnetic spectrum. So it produces majority of the light in that near IR region. That is one disadvantage of this. And the tungsten filament intensity basically varies with the fluctuation of electricity what we provide in order to heat these filaments. So there should be no fluctuations in the electric supply to these bulbs. If there is a fluctuation, then the intensity will not remain fixed, rather they tend to fluctuate a lot. So that is the tungsten filament, which is one source of radiation in UV spectroscopy. Coming to the second source of UV radiations, that is hydrogen discharge lamp. Hydrogen discharge lamp, it employs a pair of electrodes that are maintained at high voltage and are enclosed in a glass tube, and this glass tube is provided with a quartz or silica window for UV radiation to pass, Why we provide a silica or quartz window is because the UV radiations are totally transparent in this quartz window. I mean to say, unlike glass, this quartz will not absorb any UV radiations. If we make this window with glass, then the glass itself will absorb the UV radiations, and the absorbed radiation or the remaining radiation is passed after absorption. So we don't want that. So we want a total transparent window. So we construct this window with either silica or quartz so that UV radiation will pass through without any absorption. And this enclosed container is filled with hydrogen gas with relatively high pressure. We have a glass tube which is having hydrogen gas with a relative high pressure. So once we pass the electric discharge between the electrodes that are present in this glass tube, once we pass the electric discharge, the hydrogen molecules, they get excited and they tend to collide with each other to produce UV radiations. And the radiations between the hydrogen molecules resulting in pressure, resulting in pressure broadening, that results to the continuum radiation. Okay, so when the hydrogen molecules, they get excited on electric discharge, they take up the energy from the electric current, they get excited and they tend to collide with each other. Once after they collide, the resulting pressure, the high pressure that is present, that results into the broadening, and this produces the continuum radiation or the continuum pattern rather than the line pattern. And these kind of lamps are usually stable and robust and are widely used. We can replace this hydrogen gas with the deuterium gas, so that if you use deuterium instead of hydrogen, the emission intensity is increased as much as 3 times than the hydrogen discharge lamp. Since deuterium lamps or deuterium is expensive, we have hydrogen as an option here. So this is one of the good source of UV radiations that we have so far in UV spectroscopy. Coming to the next source, that is deuterium lamp. As I mentioned previously, it is same as the hydrogen discharge lamp, but instead of hydrogen gas, if you are using deuterium gas, then this lamp is called as deuterium lamp. The deuterium is used instead of hydrogen. As I mentioned, the emitted intensity of this deuterium lamp is 3 to 5 times higher than the hydrogen lamp. You can see the image here where there is an evacuated container having deuterium gas with high atmospheric pressure, and we have some electrodes, and these electrodes are basically used to excite the gas molecules so that they collide with each other and they generate the UV visible radiations. Coming to the next, that is xenon discharge lamp. The xenon discharge lamp looks somewhat like this, where we have 2 different electrodes like anode and cathode, which are separated with some certain distance, usually 8 mm distance between these 2 different electrodes, and these 2 electrodes are enclosed in a glass tube that contains xenon gas, and this xenon gas is enclosed in this container under high atmospheric pressure, that is usually from 10 to 30 atmospheric pressure. On applying a high voltage between these 2 electrodes, an intense arc is formed, thus producing the ultraviolet light. And here we have a demerit, that this xenon discharge lamp, it gets heated up too early due to high voltage what we use for discharging electricity here, and due to this we need to have some thermal insulation across this particular setup. So commercially available xenon discharge lamp, they have some thermal insulations around this entire setup. Here you can see actual xenon lamp This Xenon discharge lamp, in day-to-day life, we find them in theaters where they use this kind of lamps in the projectors. And the the Xenon discharge lamp is much efficient when compared to the previous radiation sources, and the intensity of the ultraviolet radiations what this xenon discharge lamp produces is much greater than that of the hydrogen discharge lamp. Coming to the mercury arc lamp, the mercury arc lamp is somewhat like this, wherein which it is again an evacuated tube which contains mercury vapors, and these vapors are stored under high pressure, and the excitation of these mercury vapors is done by electric discharge by using the electric supply. And this kind of mercury arc lamp is not suitable for continuous spectra because it gives the sharp or the band lines, okay, the sharp lines or the bands. This does not, or this kind of source of radiation, that is mercury arc lamp, does not produce the continuous spectra. And generally the low pressure mercury arc lamp we use to calibrate the UV spectrophotometric instrument, and the high pressure mercury arc lamp we don't usually use because they don't produce a continuum source or continuum spectra. And if you see here, here there is a evacuated glass tube which is made up of some electrodes, and these electrodes will be supplied with electric current, and that electric current is sufficient enough to excite the mercury vapors which is mixed with argon, and these mercury vapors on excitation they tend to emit the UV visible radiations. That was all about the sources of radiations what we have in UV spectroscopy. Coming to the monochromators, which is the next component in the instrumentation of UV spectroscopy. Monochromators, why we use them? We use these monochromators to isolate the radiation of the desired wavelength from the wavelength of the continuous spectra. What does that mean? If you want to isolate one particular region of wavelength from the continuum source, we usually go for monochromators, and these monochromators allow us to end up with the range of wavelength that is required for analysis. Coming to the types of monochromators, coming to the kind of monochromators we have three different types of monochromators. The first one is the filters, the second one is the prisms, the third one is the gratings. And the filters are having band pass or bandwidth of plus or minus 20 to 30 nanometers, and the gratings, the prisms have band pass as less as 0.5 nanometers, and gratings you can see they have band pass as small as 0.1 nanometer. So what does this mean? Among all these monochromatic devices, the gratings are the superior one compared to the previous, that is prisms and filters. So when I speak about the bandwidth or the band pass, what does that really means? Here is an image which is helping us to understand what we really mean by band pass or bandwidth. I want to bring your attention to the first peak on this image. Here we can see the peak is being covering from the region 555 to 595 nanometer, and we are taking the distance at half the width, or I mean at the half the distance of the peak height. Suppose if this is the peak height, we are measuring the distance exactly at the half distance, and we call that instrumental bandwidth. At this particular distance, half distance, we call it as instrumental bandwidth. And if you see in this first particular peak, the instrumental bandwidth is almost the 50 nanometer, which is overlapping on green and orange region of the spectrum. And if you see the second peak where the bandwidth is 20 nanometer, here the instrumental bandwidth is not overlapping between the green and orange, rather it is limited within the yellow region of the electromagnetic spectrum. So we are trying to exclude the green and orange, which are the wavelengths or the different wavelengths than what we are actually intending to use, which is yellow. Okay. So if the bandwidth is less, then we can focus on the region what we are actually looking for. And if you have a very narrow bandwidth of 0.1 nanometer, you can see the peak is the smallest, or it is the leanest peak, and the light beam is suitable for the most accurate analysis. Here, although the light beam appears to be single, it will not give you the accurate analytical results because some of the wavelengths are still in the overlapping region. Here, the color, the range, there is a range of colors in the light beam. We have green, we have yellow, we have orange, and that is a mixed wavelengths what we have. We will now discuss all these three monochromatic devices what we have. First we'll discuss filters, then prisms, then the grating. So this image or this particular slide, I have taken all these three monochromators, that is filters, prisms and grating in one slide, and I will try to explain all this so that we can understand on a comparative basis. So this particular image is the wavelength selector, which is the filter, and you can see there is the light beam or the source of radiation which is being passed through this wavelength selector, which is a filter wheel, and this filter wheel is having certain filters which is having a sort of a fixed band pass, where in which they allow a particular wavelength region of light to pass through. For example, here you can see a light beam which is having all the wavelengths, and after passing through the filter, only one particular beam is filtered off, which is totally green in color. Previously it was having the mixture of colors, but after passing through the filter it is having only one particular color. So what is the job of this filter? The filter usually allows one set of wavelengths to pass through, and that wavelength is having a bit broader bandwidth. So this is the kind of wavelength selector, which is filter, what we use. In order to shift from one wavelength to the other wavelength, we usually rotate this wheel. So that we will shift for the next filter, which is blue, and we can also shift for the next filter, which is red, and we can also shift for the next filter, which is purple. Okay, all of these filters will allow one particular wavelength that is assigned to them. Okay, so the green filter will allow only green light to be filtered off, the blue will allow only the blue light, and the red will allow only the red light to be filtered, and the purple will allow only the purple radiation to be filtered. So it usually operates in the visible region, and this filters, the effective band pass is usually the 50 nanometer, and they are less accurate instrument. Coming to the prisms. The prisms, it is the simple prism what we usually did an experiment when we were in school. We used to do this very simple experiment with these prisms, where we used to take this prism to sunlight, and we used to have the sunlight split into the composite wavelengths, and that was a sort of experiment which we used to do in our school days. So the prism is made up of glass, or also it is made up of quartz or fused silica, and quartz is the best choice for the UV spectrum, or if you are working the UV spectrum, the quartz is the best option. Here we can see the white light is passed through the glass prism, and there is a dispersion of this polychromatic light. We call this white light as a polychromatic light, there is a dispersion happening of this polychromatic light into the rainbow colors. This is the rainbow colors. Now if you rotate this prism, the different wavelengths of spectrum can be made to pass through the exit slit. This is a slit which allows one particular wavelength to pass through. Here you can see the blue color wavelength is being passed. If I twist this prism or rotate this prism a bit, I can allow the red light or I can selectively allow the yellow light to pass through. So that is how the prism works. And the effective wavelength depends on the dispersive power of the prism material and the optical angle of the prism. What is the angle here? That also matters. Usually these prisms are of two different types. The one which I have shown is the refractive type of prism. We also have the reflective type. Okay, rather than having a triangle, it will be made up of another triangle wherein which the one side will be 90 degree, the other two sides will be 30 degrees. But whereas in this triangles, all the three angles are of 60 degrees. So I mentioned the refractive type and the reflective types are the two different prisms what we have. The one I have shown here is the refractive type, which has 60 degrees of optical angle, and it can be adjusted so that on rotation the emerging light is allowed to fall on the exit slit. Coming to the next one, that is grating or the diffraction grating, which is most widely used in all of the instruments which are available commercially these days, and these are the most effective in converting a polychromatic light into monochromatic light. Here you can see a white light is being passed and made to fall on this diffraction grating, and the white light is split into the rainbow colors, and one particular wavelength or one particular color of light can be separated from the entire spectrum. The resolution is as less as 0.1 nanometer. We saw it previously. It can be achieved, the lowest resolution can be achieved, or the best resolution can be achieved by using these gratings. And these gratings are usually of two different types. The one I have shown is the diffraction grating. The other one we have is the transmission grating. And the diffraction grating usually consists of a large number of parallel lines. Here you can see the serrated edges. These are the parallel lines or the grooves what we call, and usually about 15,000 to 30,000 grooves will be there in 1 inch space. And these grooves they are drawn on a surface, and on these grooves they polish these grooves with a high reflective surface, usually the aluminum. They use these grooves, or they take an aluminum plate and they make some parallel grooves. I said around 15,000 to 30,000 grooves, and they polish them so that the white light is diffracted very efficiently. And they further make the surface very reflective. As I mentioned, on the aluminum surface they again deposit the aluminum powder in order to increase the diffraction power of this particular surface. And the next one, as I mentioned, is the transmission grating. The transmission grating is similar to the diffraction grating, but the refraction takes place instead of reflection. Okay, that is what we mean by transmission grating.